Welcome back. Here is a situation you will meet constantly in the real world. You write down a system of linear equations, ax equals b, and it has no solution, not because you made a mistake, but because there are more equations than unknowns and the data simply doesn't line up. Measurements have noise. 10 points that should sit on a line never quite do. So the exact system is hopeless. But hopelessness is not the end of the story. We change the question. Instead of demanding ax equals b exactly, we ask, which x makes ax as close to b as we can possibly get? That is the least squares problem, and its answer is one of the most heavily used results in all of applied mathematics. The beautiful part is that we already have the tool. The closest reachable vector is a projection, and the condition for it is the normal equations we met 2 episodes ago. Today, we turn projection into a fitting machine and use it to draw lines and curves through messy data. Let's name the situation precisely. A system is called overdetermined when it has more equations than unknowns. In matrix terms, A is m by n with m bigger than n, tall and skinny. Picture 10 data points and only 2 unknowns, a slope and an intercept, that's 10 equations, 2 unknowns. Why is there usually no solution? Because the right-hand side B lives in m-dimensional space, but the column space of A, everything A can possibly output, is at most an n-dimensional slice of that space. A small flat sheet inside a big room. A typical B simply isn't on the sheet. An exact solution exists only in the lucky case that B happens to lie in the column space. When it doesn't, the usual case, we stop chasing equality and chase the smallest possible miss instead. We define the residual, r equals b minus ax, the vector of leftover errors, and our whole goal becomes making the length of that residual as small as we can. Here is the key insight, and it is pure geometry. No matter what x we choose, the output ax is always some vector in the column space, that flat sheet of reachable targets. We can't reach b, but we can ask which point on the sheet is closest to b. And we answered that 2 episodes ago, the closest point in a subspace to an outside vector is its orthogonal projection. So the closest reachable target is the projection of b onto the column space, call it p. The best x hat is then the one whose output ax hat equals that projection. When we make that choice, the residual, b minus ax hat, equals b minus p, which is exactly the projection error, and the projection error is perpendicular to the column space. That's the whole principle. Minimizing the length of the residual is the same as making the residual perpendicular to the column space. The shortest path from a point to a plane is always the perpendicular drop. Now let's turn that perpendicularity into algebra. We need the residual to be perpendicular to every column of A. Stack all those conditions into one statement, A transpose times the residual equals the 0 vector. Write the residual as b minus ax hat, multiply through and rearrange. Out come the normal equations. A transpose A times x hat equals A transpose B. These are the same normal equations that defined projection 2 episodes back, and that is not a coincidence, it is the entire point. If the columns of A are independent, the matrix A transpose A is invertible, in fact symmetric and positive definite, very well behaved, so we can solve directly, x hat equals the inverse of A transpose A times A transpose B. And if you multiply that by A, you get A times the projection matrix times B, which is exactly the projection of B, so least squares isn't merely related to projection. Least squares is projection, wearing the costume of a fitting problem. Let's see where the name comes from. The length of the residual, squared, is the sum over all the equations of each individual error squared. Each entry of the residual is the gap between what we wanted, bi, and what we got, the ith component of ax. Square each gap, add them all up. Minimizing the length of the residual is the same as minimizing that sum of squared errors, which is why the method is called least squares. Why square the errors rather than, say, take absolute values? 3 reasons. Squaring makes every error positive so they can't cancel out. It penalizes large misses much more heavily than small ones, pulling the fit toward the bulk of the data. And it's smooth, so you can attack it with calculus. In fact, if you take that sum of squares, treat it as a function of x, and set its gradient to 0, the standard calculus minimization, you rederive the exact same normal equations. Geometry and calculus hand you the identical answer, which is always a reassuring sign. A practical note that ties the section together. In principle, you solve least squares by forming A transpose A and inverting it. But forming A transpose A squares the so-called conditioning of the problem, which can badly amplify rounding errors. There's a much better way using last episode's QR factorization. Substitute A equals QR into the normal equations. On the left, you get R transpose, Q transpose QR, but Q transpose Q is the identity, so the middle vanishes. On the right, you get R transpose Q transpose B. Cancel the common R transpose from both sides, it's invertible. and the whole thing collapses to a beautifully simple equation, r times x hat equals q transpose b. Since r is upper triangular, you finish by back substitution, no inversion at all. You get the identical best fit x hat, but with far better numerical behavior. This QR root is what real least squares software does under the hood, which is exactly why we built QR before we built least squares. Let's be precise about when this works. A least squares solution always exists no matter what, because the projection of B onto the column space is always defined. There's always a closest point. What can fail is uniqueness, and that depends on the columns of A. If the columns are independent, A transpose A is invertible and x hat is unique. One best answer. But if the columns are dependent, A transpose A is singular, and there are infinitely many x hat that all produce the same best fit, the same projection. The outputs agree, the coefficients don't. The standard fix is to pick, among all those equally good solutions, the one of smallest length, using an object called the pseudo-inverse, written A with a plus sign. Then x hat equals A plus times B gives a single canonical answer. We can't build the pseudo-inverse properly yet. It comes from the singular value decomposition, which is the climax of this section. For now, just know, a best fit always exists, and dependence only affects whether the coefficients are pinned down. Let's make this concrete with the most common application. Fitting a straight line to data. Suppose we believe y is roughly a linear function of x, y equals c plus dx, with c the intercept and d the slope, and we have a bunch of data points. Each point gives us one equation, c plus d times that point's x value should equal its y value. Stack all those equations and you get a matrix equation. The matrix A has two columns, a column of all ones, which multiplies the intercept c, and a column of the x values, which multiplies the slope d. The unknown vector holds c and d. The right-hand side b is the column of y values. With 10 points, that's 10 equations and 2 unknowns. Overdetermined, no exact solution because real points never line up perfectly. So we don't solve ax equals b. We solve the normal equations, A transpose A times the vector c, d equals A transpose b, and out come the best fit intercept and slope. This is the picture everyone has seen, now with the linear algebra behind it. The navy dots are the data, scattered, trending upward, but clearly not sitting on any single line. The bold gold line slicing through the cloud is the line of best fit, the one our normal equations produce. Now look at the short red vertical segments connecting each data point to the line. Those are the residuals, the vertical gaps between what the data actually is and what the line predicts. Some points sit above the line, some below, so the residuals point up or down. Least squares chooses the one line that makes the total squared length of all those red segments as small as possible. Tilt or shift the line any other way and the squared residuals add up to more. And here's the connection to the geometry. Stack those vertical residuals into a vector, and you get exactly the error vector b minus ax hat, the very thing that's perpendicular to the column space. The vertical gaps you see and the perpendicular projection error are the same object, viewed two different ways. This second figure shows the same fit from the geometric side, and it's worth holding both pictures in your head at once. The light blue tilted plane is the column space of A, everything we could possibly produce as AX, every candidate fit. The bold navy vector B rising out of the plane is the data. It doesn't lie in the plane, which is exactly why no exact solution exists. We drop straight down from B onto the plane. The green vector landing flat in the plane is AX hat, our best fit, the projection of the data onto the space of achievable outputs. The gold dashed segment connecting B down to its shadow is the residual, and the little red square shows it meeting the plane at a right angle. The residual is perpendicular to the column space. So the flat scatterplot picture and this geometric picture are two views of one act. Fitting a line is dropping the data vector perpendicularly onto the column space. Regression is projection. Let's fit an actual line. 3 data points, 0, 1, 1, 2, and 2, 2. We want the best line, y equals c plus dx. Build A, its first column is all ones. Its second column holds the x values 0, 1, 2. The right-hand side B holds the y values, 1, 2, 2. Now form the normal equations. A-transpose-A is a 2 by 2 matrix. The top row is 3, 3, the bottom row is 3, 5. A-transpose-B is 5, 6. Solve A-transpose-A times the vector c, d equals A-transpose-B. The solution is c equals 7 sixths and d equals 1/2. So the best fit line is y equals 7 sixths plus 1/2 x. Notice the slope is 1/2 and the intercept is about 1.17, a sensible line through 3 points that rise then flatten. No exact line passes through all 3, but this one minimizes the total squared vertical error, and the normal equations handed it to us in a few steps of arithmetic. Now the check you should always run. Take the best fit line from the last example and compute what it predicts at each x. At x equals 0, it predicts 7/6, at x equals 1, 5/3, at x equals 2, 13/6. Subtract these predictions from the actual y values to get the residual vector, -1/6, 1/3, -1/6. Now verify that this residual is perpendicular to both columns of A. Dot it with the column of 1s, -1/6 plus 1/3 minus 1/6, which sums to 0. So the residuals cancel out, the line is balanced. Dot it with the column of x values, 0, 1, 2, 0 times -1/6 plus 1 times 1/3 plus 2 times -1/6, which is 1/3 minus 1/3, also 0. Both dot products vanish, which is precisely the statement A transpose times the residual equals 0, the normal equation satisfied. The residuals summing to 0 and being uncorrelated with x are the geometric signature of a correct least squares fit. One more to show how far this reaches. You might think least squares only fits straight lines, but it fits any model that's linear in the unknown coefficients, and that includes curves. Say we want a parabola, y equals c0 plus c2x squared. Each data point still gives one equation, and we build A with 3 columns now, a column of 1s, a column of x values, and a column of x squared values. The unknowns are the 3 coefficients c0, c1, c2. Then we solve the very same normal equations, A transpose A times x hat equals A transpose B. Here's the subtle but crucial point. The model is nonlinear in x. It has an x squared term, but it is perfectly linear in the coefficients we're solving for. And linearity in the unknowns is all least squares ever requires. Want a cubic? Add an x cubed column. Want sines and exponentials in your model? Add those columns. The same projection machinery fits them all. That generality is why least squares is everywhere in science and machine learning. A bit of history, and it's a good one. In 1805, Adrien Marie Legendre published the method of least squares in an appendix to a paper on comet orbits, the first time it appeared in print. 4 years later, Carl Friedrich Gauss published his own treatment and claimed he had been using the method since 1795, a full decade earlier. That sparked one of the most famous priority disputes in the history of mathematics. But Gauss added something genuinely new. He connected least squares to probability, showing it's the optimal estimate when errors follow the bell-shaped normal distribution. And he had a spectacular demonstration. In 1801, astronomers briefly spotted the dwarf planet Ceres, then lost it behind the sun. Gauss used least squares on the sparse observations to predict where it would reappear, and when telescopes pointed there, Ceres was waiting. Today, the method those two giants quarreled over runs billions of times a day, inside every regression, every statistical model, every machine learning fit. Let's recap. The problem, an overdetermined system AX equals B, where B lies outside the column space of A, so there's no exact solution. The idea, instead of solving exactly, minimize the length of the residual B minus AX, which means projecting B onto the column space, the closest reachable target. The condition that the residual be perpendicular to every column gives the normal equations, A transpose A times x hat equals A transpose B. Solving them yields x hat equals the inverse of A transpose A times A transpose B, and the fitted values AX hat are exactly the projection of B. To fit a line, use a column of 1s and a column of x values. To fit a curve, just add an x squared column or higher powers. Anything linear in the coefficients works. The residuals are the error vector, and their total squared length is as small as possible. Historically, Gauss and Legendre gave us this around 1800. Next episode, we turn to the symmetric matrix A transpose A that sits at the heart of all this and the spectral theorem that governs it. Today we learned to solve the unsolvable. When a system AX equals B has more equations than unknowns, the vector B usually lies outside the column space of A, so no exact solution exists. The least squares idea is to find the x that makes AX as close to B as possible, minimizing the length of the residual, B minus AX. Geometrically, the closest point in the column space to B is the orthogonal projection of B onto the column space, and the best x is the one whose output equals that projection. Demanding that the residual be perpendicular to every column of A gives the normal equations, A transpose A times x hat equals A transpose B. That is the same projection condition from 2 episodes ago, now read as a recipe for fitting. Solving the normal equations gives the best fit coefficients. We use this to fit a straight line to scattered points, where x hat holds the slope and intercept, and to fit a parabola, where the same machinery handles a curve. The residuals, the little vertical gaps between the data and the fit, are exactly the error vector, and their total squared length is as small as it can possibly be. Next episode, we study the symmetric matrix A transpose A in its own right and meet the spectral theorem. If you got something out of this, please like the video, drop a comment with what clicked for you or what didn't, and subscribe for more educational videos. Every like, comment, and share helps push this work to more learners, which is what this channel is really about. Thanks for watching. See you in the next one.